Hi everyone, Stack Lessons again, 20 questions for you today, all about AI search scale limits, MLflow 3 model lifecycle, and RAG retrieval metrics. Standard 10-second countdown on each one. Try not to peek at the answer before you commit. Good luck. Ready. Question 1. Track every qualifier. A generative AI engineer at Creston Legal is tuning BM25 parameters for the hybrid search component of a case research assistant. Keyword-dense documents that repeat important legal terms dozens of times are consistently outranking more focused, concise answers. The engineer wants to reduce the influence of keyword repetition without altering length normalization behavior. The current configuration has K1 equals 1.5 and B equals 0.75. Which single parameter change achieves this? Select one. Review the answer choices on screen. The correct answer is option D. Here is why B is a deliberate distractor. The K1 parameter controls term frequency saturation, the rate at which additional occurrences of a term stop, meaningfully increasing a document's score. Decreasing K1 causes saturation to kick in sooner, so the 50th occurrence of a legal keyword contributes far less marginal gain than it would at a higher K1 value. This directly resolves the problem of keyword-dense documents outranking focused answers. Increasing K1 raises the saturation ceiling, making each additional keyword occurrence more influential, which is the opposite of what is needed. The B parameter governs document length normalization, rather than term frequency behavior. Increasing B would penalize longer documents broadly, but would not specifically dampen the influence of keyword repetition, and the engineer explicitly wants length normalization left unchanged. Decreasing B reduces length normalization entirely, which would amplify the existing advantage that long, keyword-heavy documents already enjoy. Let's slow down here. BM25 has two knobs and the exam wants you to know exactly which does what. Imagine a document that says liability 50 times and a shorter doc with the precise answer. BM25 scores both, but which knob controls repetition's power? That's K1. It sets how fast repeated hits stop adding score. At K1 equals 1.5, that 50th liability still gives a meaningful boost. Drop K1 lower, and the score flatlines after a few occurrences. Repetition stops paying off. Now B is tempting. It also affects scoring, but it controls length normalization, not repetition. The question explicitly says leave length normalization alone, so B is off the table entirely. The trap is thinking both parameters work the same way, only K1 controls repetition's ceiling. Ready? Careful on question 2. This one has a trap. A generative AI engineer at Callaway Tech is building a content compliance platform for a video streaming service. The platform must inspect both thumbnail images and short video clips for policy violations in a single model call, without a separate pre-processing pipeline. The engineer must use a foundation model API model. Which model should they select? Select one. Review the answer choices on screen. The correct answer is option A. One native modality separates Gemini from the others. Gemini 2.5 Flash is the correct choice because Gemini family models available through the Foundation Model API natively support all four input modalities: text, image, video, and audio. This native video support is the decisive differentiator that allows a single model call to process both thumbnail images and video clips without any additional pre-processing pipeline. Claude Sonnet 4.6 supports text and image inputs within the Foundation Model API, but does not support video as an input modality, making it incapable of natively ingesting video clips for policy analysis. Llama 4 Maverick similarly supports text and image inputs only, and cannot process video content without a separate frame extraction step, that reroutes the workload outside the model's native capabilities. BGE Large is an embedding model that produces vector representations for retrieval and similarity search. It cannot interpret visual or video content, cannot detect policy violations, and cannot generate structured text output of any kind. Ready? Let's open question 3. A generative AI engineer upgraded a Databricks workspace to MLflow 3 and observed that calls to MLflow.register_model without an explicit registry URI argument are now routing models to a different destination than before the upgrade. Where are the models now being registered, and what caused the change? Select 1. Review the answer choices on screen. The correct answer is option A. MLflow 3 changed one default that breaks migrated code. MLflow 3 changed the default registry URI to Databricks UC, which routes all model registrations that omit an explicit registry URI to Unity Catalog. Before this change, the default destination was the workspace model registry. Code written for earlier MLflow versions that does not specify a registry URI will now land in Unity Catalog automatically after the upgrade, which explains the observed change in destination. The Databricks feature store is not a model registration destination for MLflow. MLflow 3 did not introduce a local DBFS registry as the new default. Unity Catalog integration was not deprecated. It became the default and is the recommended model registry going forward in MLflow 3. Let us switch gears. Let's look at question 4. Quick check. A generative AI engineer at Stonebridge AI is logging the results of a fine-tuning run using MLflow. The fine-tuned model checkpoint is 7 GB in size. The engineer calls MLflow.log_artifact to upload the checkpoint to the run. What will happen? Select 1. Review the answer choices on screen. The correct answer is option C. 5 GB, hard ceiling, no auto split. MLflow enforces a 5 GB per artifact file size limit. Attempting to log a checkpoint that exceeds this threshold causes the upload call to fail rather than silently truncating the file or partially uploading it. MLflow does not automatically chunk files, split uploads, or compress artifacts to accommodate oversized payloads. The limit is a hard upload cap. To work around this constraint, the engineer would need to reduce the checkpoint size, split it into multiple smaller files each under 5 GB, or store the artifact externally and log a reference path instead of uploading the binary directly. Let us switch gears. Question 5. Avoid the familiar but wrong answer. A generative AI engineer at Holloway Systems is configuring a Databricks AI Search index that supports both approximate nearest neighbor vector search and hybrid keyword plus vector search. A product manager asks about the maximum number of results each mode can return per query. Which answer is correct? Select 1. Review the answer choices on screen. The correct answer is option C. ANN and hybrid carry completely different result ceilings. Databricks AI Search imposes different result limits depending on query mode. Pure approximate nearest neighbor vector queries can return up to 10,000 results, enabling broad semantic retrieval across large corpora when needed. Hybrid searches that combine BM25 keyword matching with vector similarity, as well as full text-only search queries, are each capped at a maximum of 200 results per query. This asymmetry reflects the greater computational complexity of combining and re-ranking multiple relevant signals in hybrid mode. Engineers designing pipelines that require large result sets for downstream re-ranking should use pure ANN retrieval where feasible, or apply metadata pre-filtering to narrow the candidate pool before triggering hybrid search. The first 5 locked in 3 critical thresholds. K1 governs term frequency saturation, not length. MLflow 3 now defaults to Unity Catalog silently, and hybrid queries are hard capped at 200 results, while pure ANN reaches 10,000. Keep your focus here. Let's check question 6. A generative AI engineer at Waverley Systems is building a LangChain RAG application using a Databricks vector search vector store connected to an existing Delta Sync index. The engineer needs to produce a LangChain compatible retriever object configured to return the top 5 most relevant document chunks per query so it can be composed into a retrieval QA chain. Which method called on the Databricks vector search instance creates this retriever? Select one. Review the answer choices on screen. The correct answer is option A. Similarity_search returns a list, not a retriever object. LangChain vector store implementations, including Databricks vector search, expose an as_retriever method that wraps the underlying store in a vector store retriever object conforming to the base retriever interface required by LangChain chains such as Retrieval QA. The search_quarks dictionary accepts parameters including k, which controls how many results are returned per query, allowing the retriever to be composed dynamically into a chain. Calling similarity_search performs an immediate one-shot lookup and returns a list of document objects, but the result is not a retriever object and cannot be invoked dynamically by a chain on each new user input. There is no get_retriever method on the Databricks vector search class or in the standard LangChain vector store API. The create_retrieval_chain function is a top-level LangChain utility that assembles a chain from an existing retriever and an LLM, but it is a standalone function rather than a method callable on a vector store instance. Keep your focus here. Let's check question 7. A generative AI engineer is building a RAG system for a medical textbook application. Physicians report that answers sometimes miss critical context when treatment protocols span multiple paragraphs. The current configuration uses 400 token fixed-size chunks with no overlap. What change would most directly resolve the context continuity issue at chunk boundaries? Select one. Review the answer choices on screen. The correct answer is option C. Overlap is the surgical fix for boundary gaps. Adding overlap between adjacent chunks is the targeted fix for context loss at chunk boundaries. When a treatment protocol spans a boundary, overlap ensures the tail of one chunk and the head of the next both contain the transitional content, so retrieval can surface a complete protocol even when only one chunk is returned. Switching to semantic chunking repositions boundaries based on topic similarity, but does not guarantee that all protocol spanning content will fall within a single semantic segment, and it adds significant computational cost without directly addressing the boundary problem. Reducing chunk size to 100 tokens creates more boundaries, worsening fragmentation rather than alleviating it. Increasing chunk size to 2048 tokens risks exceeding many embedding models' context windows, and introduces noise from unrelated content within each chunk, degrading retrieval precision. Okay, question 8. Picture the scenario first. A generative AI engineer at Orion Technologies is running a series of experiments comparing different prompt templates and retrieval configurations for a customer service RAG application. They want all metrics, parameters, and execution traces to be automatically linked to the model artifact, so that full traceability is preserved when the model is promoted to production. Which MLflow 3 capability provides this automatic linkage across development phases? Select one. Review the answer choices on screen. The correct answer is option D. LoggedModels auto-link everything without extra association calls. MLflow 3 introduces LoggedModels, which automatically capture metrics, parameters, and execution traces across all development phases without requiring manual association calls for each artifact. When a logged model is promoted to a Unity Catalog model version, all of its associated performance data becomes visible directly on the UC model version page, providing seamless traceability from experiment to deployed model. Manual lflow.log_metric calls require the engineer to explicitly associate each metric with the correct run and artifact, which is error-prone across many configurations. Experiment tags attach labels to the experiment container itself and do not propagate automatically to registered model versions or link artifacts to their performance history. Model signatures define input and output schemas for type enforcement, and do not carry evaluation metrics or trace data. Okay. Question 9. This is a distractor check. A generative AI engineer at Verilex Media is building a semantic search system over a global media archive, containing approximately 1.5 billion embedded documents at 768 dimensions. After benchmarking, the team confirms that standard AI search endpoints cannot support the full corpus. A stakeholder presentation requires clearly communicating two properties of the alternative endpoint type. Which two characteristics of storage-optimized endpoints are accurate? Select 2. Review the answer choices on screen. The correct answers are Option A and Option C. Option C inverts the latency direction. Read carefully. Storage-optimized endpoints are purpose-built for two distinct advantages relevant to this migration. First, they support corpora exceeding 1 billion vectors, directly addressing the 1.5 billion document archive that exceeds the standard endpoint ceiling of approximately 320 million vectors at 768 dimensions. Second, they deliver 10 to 20 times faster index build and update speeds compared to standard endpoints, which is a significant operational improvement for ingesting and refreshing a corpus at this scale. Storage-optimized endpoints introduce approximately 250 milliseconds of additional query latency rather than reducing it, because retrieving vectors from disk-optimized storage is slower than serving from memory-resident indexes. The choice between direct access and delta sync index types governs how embeddings are supplied and is independent of whether the endpoint is standard or storage-optimized. Cross-availability zone replication is not a characteristic specific to storage-optimized endpoints. Let's slow down here. Storage-optimized endpoints have some tricky trade-offs worth knowing cold. Picture a media company with 1.5 billion archive documents. Standard AI search endpoints hit a ceiling around 320 million vectors. Storage-optimized blows past that. It supports over a billion vectors at 768 dimensions. That's the first correct answer. Index builds also get a big speed boost, 10 to 20 times faster, so a billion vector corpus loads in under 8 hours. That's the second. Now the traps. Query latency gets about 250 milliseconds slower. Vectors sit on disk, not in memory. The index type choice is completely separate from endpoint type, and cross-zone replication is not a feature of storage optimized. The question rewards knowing the two real wins: scale and fast indexing. Here we go. Question 10. Eliminate before you select. A generative AI engineer at a healthcare company is deploying a patient support chatbot through Databricks AI Gateway. Compliance requirements specify that personal information such as email addresses, social security numbers, and phone numbers must never appear in requests transmitted to the LLM or in responses returned to users. The engineer wants to use native AI Gateway guardrail capabilities. Which two guardrail modes does AI Gateway support for handling PII? Select 2. Review the answer choices on screen. The correct answers are Option A and Option B. Redact versus block, only these two modes are native. AI Gateway provides two native guardrail modes for PII. PII detection and redaction automatically identifies personal information including email addresses, social security numbers, and phone numbers, then replaces them with placeholder tokens before the content is sent to the underlying LLM. This allows the conversation to continue with sensitive data removed. PII blocking takes a stricter approach by detecting PII in either the incoming request or outgoing response and rejecting the entire message rather than allowing a redacted version through, enforcing zero tolerance where any detected PII causes the transaction to fail. PII encryption is not a supported AI Gateway guardrail mode. PII anonymization using synthetic data replacement is not a built-in AI Gateway feature. PII masking that allows original data to pass through to the LLM would directly violate the compliance requirement and is not a documented AI Gateway capability. Let's slow down here. The PII guardrail modes are exactly what this question tests. Picture a patient messaging your chatbot, "My social security number is 123456789, help me." AI Gateway hits a fork in the road. Redaction swaps that number with a placeholder token. The LLM sees clean text and the chat keeps going. Blocking takes a harder stance. It kills the whole request and sends back an error. Those are the only two built-in modes. Encryption, not a native feature. Synthetic fake data, also not built in. The exam loves plausible-sounding distractors. The real fork is simple: swap and continue or hard stop. Questions 6 through 10 contained 3 multi-select traps and 1 latency inversion, as _retriever wraps a store into a chain-compatible object. Similarity_search does not. Storage optimized adds roughly 250 milliseconds rather than removing it, and AI Gateway PII has exactly 2 native modes. Okay, let's get into question 11. A generative AI engineer at Northwind Analytics is deploying a Databricks AI Search index for an enterprise document archive containing approximately 1.5 billion vector embeddings at 768 dimensions. The corpus is updated nightly through large batch indexing jobs, and the team explicitly accepts slightly higher per-query latency in exchange for the ability to operate at this scale. Which endpoint type meets these requirements? Select one. Review the answer choices on screen. The correct answer is option D. Past 1 billion vectors, the choice is automatic. Storage-optimized endpoints are specifically designed for corpora exceeding 1 billion vectors. They deliver 10 to 20 times faster indexing throughput compared to standard endpoints, which is essential for nightly batch updates at this scale. The accepted trade-off is approximately 250 milliseconds of additional per-query latency. Standard endpoints support approximately 320 million vectors at 768 dimensions, far below the 1.5 billion required, making them unsuitable regardless of how many indexes are created. Partitioning across multiple indexes on a standard endpoint introduces complex query routing and does not extend total supported capacity in a coherent architectural pattern. A direct access index shifts embedding management to the caller, but does not change the underlying capacity limits of the endpoint type, and adds pipeline complexity without resolving the scale constraint. Next up, question 12. Watch for must, most, least, or except. A generative AI engineer at Fabricam Research is building a technical knowledge retrieval system where users rely most heavily on the top-ranked results and expect the most relevant documents to appear first. The team wants a retrieval metric that penalizes systems that return the right documents but rank them poorly. Which metric best captures this requirement? Select one. Review the answer choices on screen. The correct answer is option D. Penalizes poor ranking. That word is the pivot. NDCG, Normalized discounted cumulative gain, is the only standard retrieval metric that simultaneously captures relevance quality and ranking order. It assigns higher value to relevant documents appearing near the top of the ranked list, and applies a logarithmic discount to documents ranked lower, producing a score between 0 and 1 where 1.0 represents a perfect ordering. This directly penalizes systems that retrieve the right documents but place them at lower positions. Recall at K measures completeness, whether relevant documents were retrieved at all, with no sensitivity to rank position. Precision at K measures how many retrieved results are relevant but treats all positions equally. F1 at K blends precision and recall but still does not weight by ranking position. Next up, question 13. Spot the narrowing word. A generative AI engineer at Pinecrest Legal is comparing two retrieval configurations for a contract review RAG system. For this application, every clause relevant to a user query must be retrieved. Missing even a single relevant clause could result in a legal oversight. The engineer wants to select the retrieval metric that best captures this completeness requirement when comparing configurations. Which metric should they prioritize? Select one. Review the answer choices on screen. The correct answer is option B. Every clause must be found. Completeness demands recall. Recall at K measures the fraction of all known relevant documents that are present in the top K retrieved results, making it the correct metric when completeness is the primary concern. For a legal contract review system where missing any relevant clause creates serious risk, maximizing recall ensures the retrieval configuration surfaces as many relevant documents as possible within the result window. Precision at K measures the proportion of retrieved documents that are relevant. It penalizes irrelevant results, but does not capture how many relevant documents were missed entirely, which is the critical concern for this use case. NDCG at K evaluates the quality of the ranking order, rewarding configurations that place the most relevant documents first. This is valuable when users only read the top results, but it does not directly measure whether all relevant documents are retrieved at all. DCG at 10 also measures ranking quality with relevance intensity scoring on a 0 to 3 scale, and shares the same limitation as NDCG. It does not penalize missing relevant documents that fall outside the top K retrieval window. Now, question 14. This is a two-step filter. A generative AI engineer at Holloway Finance is building a RAG application for personalized investment advice. At query time, the system must retrieve a pre-computed risk tolerance score for the user from an online feature store, and also compute a real-time portfolio diversification index by applying a formula to several stored portfolio metrics. The engineer is designing the FeatureSpec configuration. Which two FeatureSpec component types should they include? Select 2. Review the answer choices on screen. The correct answers are option A and option C. 3 of 5 component names here simply do not exist. Feature Lookup retrieves pre-materialized column values from an online feature store by entity key, making it the correct component for fetching the stored risk tolerance score for a given user. Feature Function applies a use-defined transformation or formula to derive on-demand features at serving time, making it the right tool for computing the portfolio diversification index from stored portfolio metrics during the request. Feature Summary is not a valid component type in the Databricks Feature Serving API. Aggregate statistics would be pre-materialized as features through the upstream engineering pipeline, rather than computed inline within the feature spec. Feature Stream is not a feature spec component. Real-time data delivery in feature serving is handled through the online store update pipeline, not a streaming subscription defined inside the feature spec. Feature cache is not a feature spec component type. Caching behavior within feature serving is managed by the endpoint infrastructure automatically, and is not a configurable element of the FeatureSpec definition. Let's slow down here. This Select 2 question hides a trap most candidates walk straight into. Imagine you're sitting in the exam, 80% of the way through, and you spot this question. You quickly realize option A is right. Feature lookup fetches a stored score by user ID. So far, so good. Then you glance at B through E. Feature stream sounds logical for a finance app. Feature summary sounds like it aggregates transaction history. You pick one as your second answer, and you just lost half the points. Here's the fix. FeatureSpec only has 2 real building blocks: feature lookup and feature function. The other 3 names are completely invented. The word pre-computed is your signal for lookup. Applying a formula is your signal for function. The question rewards knowing both real names, not reasoning from what sounds plausible. Now for question 15. Quick check. A generative AI engineer at Holborn Systems is logging a large language model checkpoint using MLflow.log_artifact. The checkpoint directory totals 7 GB in size. What will happen when the engineer attempts to upload this artifact to MLflow? Select 1. Review the answer choices on screen. The correct answer is option C. Same 5 GB ceiling, reinforce it and move on. MLflow enforces a 5 GB maximum for individual artifact file uploads and downloads. A checkpoint totaling 7 GB exceeds this limit, causing the upload to fail. There is no automatic compression or transparent multipart splitting built into MLflow's artifact logging interface. Engineers working with very large model checkpoints must either split the artifacts into files below the 5 GB limit, use external storage systems such as S3 with direct upload, or store the artifacts in Unity catalog volumes and manage them independently outside the standard artifact logging path. Questions 11 through 15 tested metric vocabulary and API name validity. NDCG rewards rank order. Recall rewards completeness. Feature summary and feature stream and feature cache are all invented, and the 5 GB artifact cap appeared twice. That repetition signals exam weight. Now, question 16. Coming up, a generative AI engineer at Fabricom Retail is building a product recommendation engine that will index over 2 billion product embeddings at 768 dimensions. When they attempt to configure an AI search endpoint, they find that the standard endpoint configuration cannot support their data volume. What should they do to accommodate this scale? Select 1. Review the answer choices on screen. The correct answer is option A. 2 billion exceeds standard capacity by over 6 times. Standard AI search endpoints support approximately 320 million vectors at 768 dimensions, which is far below the 2 billion vectors required. Storage-optimized endpoints are designed specifically for very large indexes exceeding 1 billion vectors and offer 1020x faster indexing speed. The trade-off is an approximate 250 milliseconds increase in query latency, which is acceptable when standard capacity is insufficient. Splitting across multiple standard endpoints would require custom routing and result merging logic, adding significant complexity without resolving the underlying capacity constraint. Reducing embedding dimensions changes the semantic quality of representations and still would not allow 2 billion vectors to fit within a standard endpoint. Choosing between direct access and delta sync is an index management decision related to who manages embeddings, not a mechanism for increasing storage capacity. Let us keep moving. Question 17. Separate context from noise. A generative AI engineer at Crestwood Digital is managing a production LLM application through AI Gateway and wants to gradually roll out a new foundation model. The plan is to direct 10% of live production traffic to the new model, while keeping 90% on the existing model, allowing the team to compare quality metrics before committing to a full migration. Which AI Gateway capability should they configure? Select 1. Review the answer choices on screen. The correct answer is option C. Rate limiting controls volume. It cannot split traffic. Traffic splitting in AI Gateway allows an engineer to define multiple model routes within a single endpoint and assign percentage weights to each route. Setting weights at 10% and 90% proportionally divides live production traffic between the new model and the existing model, enabling a gradual rollout where real requests validate the new model without full exposure. Rate limiting controls the total volume of requests an endpoint, user, or group can submit per unit of time. It restricts access volume rather than routing a defined fraction of traffic to different backends and cannot implement a percentage-based split across models. PII filtering governs whether requests or responses containing personally identifiable information are allowed through a route. It is a content control mechanism with no effect on traffic distribution. Safety filters block harmful content categories such as hate speech or violence, and are unrelated to the traffic distribution mechanism needed for a gradual model rollout. Let us keep moving. Here comes question 18. A generative AI engineer at Ridgeline AI has been iterating on a summarization model using MLflow 3. During development, they logged multiple experiments as logged models, capturing evaluation metrics, hyperparameters, and execution traces at each iteration. They are now ready to move the best candidate to production by registering it in Unity Catalog. What happens to the development data captured in the logged model when it is promoted to a Unity Catalog model version? Select one. Review the answer choices on screen. The correct answer is option C. Promotion carries all logged data, nothing to reattach. When a logged model is promoted to a Unity Catalog model version in MLflow 3, all performance data captured during development, including evaluation metrics, hyperparameters, and execution traces, is automatically surfaced on the Unity Catalog model version page. This design preserves the complete development history and makes it available for governance, audit, and cross-version comparison without any additional steps. The data is not archived or hidden upon promotion. It remains accessible and is explicitly linked to the registered version. No separate API call is needed to transfer performance data. The promotion step handles this automatically as part of the lifecycle transition. The transfer is not limited to model weights. The entire logged context accompanies the model as it moves from the experiment phase into the production registry. Ready. Question 19. Keep the constraints in view. A generative AI engineer is building a RAG knowledge base from a large corpus of academic oncology research papers. The papers frequently shift topics mid-paragraph, use highly technical jargon, and have variable section lengths. Retrieval quality is the top priority, and the team can tolerate longer indexing times. Which chunking strategy should the engineer select? Select one. Review the answer choices on screen. The correct answer is option A. Mid-paragraph topic shifts demand semantic boundaries, not token windows. Semantic chunking uses embedding models to group adjacent sentences by topic similarity, producing chunks that align with natural topic shifts in the source material. This is the strongest match for academic papers that shift topics mid-paragraph, since semantic chunking respects semantic boundaries rather than imposing arbitrary split points. The trade-off is higher computational cost during indexing, but since the team explicitly prioritizes retrieval quality over indexing speed, this is acceptable. Fixed-size chunking with no overlap splits documents at arbitrary token boundaries, which frequently cuts through a single concept and degrades retrieval quality. Recursive character splitting is a more principled baseline than fixed-size chunking, but relies on character-level separators rather than semantic content, so it cannot detect mid-paragraph topic shifts. One chunk per entire document makes retrieval too coarse, flooding the context window with an entire paper in response to any query and burying the relevant passage. Ready. Question 20. Follow the operational constraint. A generative AI engineer is designing a RAG application for a retail analytics platform. The system must answer natural language questions about product descriptions and return policy documents stored as PDFs, and it must also answer precise inventory queries such as how many units of SKU 4821 are in the Chicago warehouse, sourced from a relational database. Which architecture correctly handles both data types? Select one. Review the answer choices on screen. The correct answer is option A. Vector search cannot reliably answer precise unit count queries. RAG on Databricks handles unstructured and structured data through separate mechanisms optimized for each type. Unstructured content such as PDFs is chunked, embedded, and stored in an AI search vector index for semantic retrieval. Structured data like inventory tables is best queried through a SQL interface that applies exact filters and aggregations, operations that vector similarity search handles poorly because it cannot reliably match precise numeric values, primary keys, or warehouse location identifiers. Embedding all SQL rows into a single vector index conflates retrieval paradigms and makes exact lookups unreliable. Converting SQL rows to natural language before embedding is lossy and computationally expensive, and still cannot guarantee accuracy for precise numerical inventory queries. Feature serving is designed to expose pre-computed, continuously updated real-time features at low latency, not to serve arbitrary SQL query results in a RAG retrieval loop. This one trips up a lot of people. Let's break down why two retrieval methods beat one. Imagine you're building a chat assistant for a retail company. Someone asks, "What's our return policy for electronics?" Perfect for vector search, it finds the right PDF paragraph by meaning. But then someone asks, "How many units of SKU 4821 are in Chicago?" That question needs an exact answer. Say, 247. Vector search can't give you 247. It finds text that sounds like inventory info. That's a different thing entirely. The trap in answers C and D is assuming one retrieval method handles both jobs. It doesn't. Two data types need two tools: semantic search for PDFs, SQL for exact counts. Answer A routes each question to the right tool. 3 takeaways from this session. First, storage-optimized endpoints add roughly 250 milliseconds per query to unlock billion vector corpus support. Second, MLflow 3 silently rerouted all unscoped registrations to Unity Catalog. Omitting a registry URI now behaves differently than it did before the upgrade. Third, recall at K measures completeness of retrieval, NDCG at K measures rank quality. The exam will force you to distinguish them by scenario, not definition. MLflow 3 changed to default silently. Storage-optimized endpoints trade latency for scale by design. Recall and NDCG answer different questions and the exam will make you choose. Trust the reasoning, not just the answer.